Hello and welcome back to Manifolds. And as always, many thanks to all the nice people who support this channel on Steady, via PayPal or by other means. Now, in today's part 6, we continue the topic of topology and will talk about so-called second-countable topological spaces. However, in order to understand this notion, we first have to introduce the concept of a basis of a topological space. For this, the overall idea is that we just need some subsets to generate the whole topology of our topological space. So we want an efficient way to describe our topology T. This means when we know the basis, we also know the whole topology. Hence you see, this is not a complicated idea at all, so we can immediately formulate the definition. Of course, as an assumption, we only need a topological space, so a set X, together with a topology T on X. And now we just take a collection of subsets, more precisely open subsets, which means there are elements in T. In other words, we have a subset of T we can call B. Of course here, B stands for basis. More concretely, it's called a basis or sometimes base of the topology T. There's only one property this basis should fulfill, and this can be nicely visualized here with the set X. Just assume we have an open set U here, so an element of T. And now we should be able to cover the whole set with elements from B. Of course, there could be an overlap here, but we don't hit any points outside of U. Therefore, as you can see, it might happen that we need infinitely many sets AI from B. Okay, and that's already the whole property we have to state here. This means that for any chosen open set U, we find a whole collection of open sets AI. And as I told you before, here it does not matter what the index set I here is. So we could have finitely many or infinitely many sets AI. The only important thing here is that all the AIs come from our collection B. And then the conclusion is that the union of the sets AI is the set U. So in summary, each set U can be written as such a union. And this is the defining property of a basis of a topology. Okay, then I would say, when we look at examples, you see that this is not a complicated notion at all. And as always, we should start with simple examples. Now, the simplest one you might already spot in the definition, in the case where it is possible to choose just one AI here. This is what we can do when B is simply given as the whole topology T. Then we don't gain anything, but of course this fulfills the definition. So this might not be an interesting basis, but it works for every topology T. However, the next example only works for the discrete topology on X. There, please recall, in this topological space, every subset of X is open. And therefore, we can nicely generate all sets when we just take singletons. Which means we have subsets with just one element inside. Then, if we take all these subsets, we have a basis of the topology. This shouldn't be hard to see, because each set can be written as the union of its elements. Okay, and there you see, we've started with two very simple examples. Therefore now, I think we are ready for the most important example. I really think this is an important example because we already used this while working in metric spaces. Therefore here, Xt should be the topological space given by a metric space Xd. So you know, in this example, openness here means exactly the same as openness in the metric space. As a reminder, openness there is defined by using epsilon balls. And such a ball is denoted by B epsilon x, where epsilon is the radius and x is the middle point. Now, you might already know, the idea is to look at the collection of all epsilon balls. So any middle point x is possible and every radius epsilon. And now we simply call this collection of all epsilon bolts B. And not so surprising, this B is a basis of the topology T. Indeed, this fact follows immediately from the definition of an open set in a metric space. So, not a surprise here, but we can simplify this even more when we look at a special metric space. And this one is well known, it's Rn with the Euclidean metric. Usually, just with a few words, we just say that T is the standard topology on Rn. Now, because we have a metric here, we can use the same base as before, but now with epsilon bolts defined by the Euclidean metric. Okay, in this sense you would say the basis looks the same, we go through all points and through all possible epsilons. However, it turns out we don't need all the points because we have a dense subset. It's sufficient to look at rational points because for all other points we can get as close as we want. And in the same sense, the radius epsilon can also be just a rational number. However, of course, it still needs to be greater than 0. Okay, now you might ask, what is the advantage of this basis in contrast to the one we had before? Of course, we have less elements here, but still infinitely many. However, in fact, we have reduced the size of the infinity. This set here is now countable. It only has countably many elements. So the set is infinite, but it's the smallest infinity we have. So this is very nice, because when we work with this basis, we only need unions with countably many elements. Therefore, we can say this is a nice property of the topology. And this is what we should fix in the next definition. There, the whole topological space with this nice property gets a new name. This is what I already told you in the introduction. The space is called second-countable. And we say this if there is a countable basis of the topology T. Hence, we can say Rn with the standard topology is second-countable. Okay, now you might ask, why is it called second-countable? Is there also a first-countable? Indeed, there is, but we will only need second-countable spaces here. We will see this soon when we introduce manifolds. In fact, a manifold will be defined as a topological space that is second-countable, also a Hausdorff space, and that also fulfills a third property. However, this third property is a topic for another video. Therefore, I really hope that I see you there. Have a nice day. Bye.